SwayamPrabha. Digital India. Educated India.
Hi, so welcome back. So what we have been looking at so far are various examples of turbulent flow, and so we've looked at, say, flow coming out through pipes, right? Turbulent flow, exhaust gases coming out from exhaust outlets, from factory sheds, etc. So we've looked at a lot of examples of that. Now our job here is to now put some math into all of that, right? What if somebody asked us to design, a plume like that from where we would have some exhaust gases, right? So he says, make sure that I have, plumes coming out at this rate and in this way, how do I go about that? So how do I study? In the sense, when I say, if somebody asks, for example, that you have exhaust gases coming out from this plume, right? And these are all toxic gases, and some things that we should not be near that because they are harmful, right? Then what should be the area, right, which is safe enough? Where should be the area around that plume, which I should sort of demarcate, such that if I place human habitation beyond that, they should be safe enough and they should not be affected by such toxic gases or harmful gases that are coming out of those things. How would I answer that question, right? So those are the kind of things. Then again, you have these pipes through which there is used water, dirty water, which is being discharged. It is full of materials that are harmful or which are basically to be discarded. Now they are being thrown somewhere. Okay, now you always see these things outside of the city, right? You always see things away from more or less habitation, right? Now who decides how big that distance should be, how big that area should be? Those are the questions, therefore, we must be ready to answer, right? For example, if I so let us see. So if I have, say, something like this. So what we're going to do today is look at the math that we put and some technical definitions that we will use in that. Okay. So one is this thing that we it's a very standard basic problem, which is that of the round jet. Okay. So what I mean by that is basically flow is coming out of a flow. There is a jet which is being which is coming out. Okay. So let's just say I have some kind of a, okay, I think what I'm going to do is go down here a little bit. Okay. Okay. So let's just say that I have a plume which is like this, right? Let me draw an axis system there. Okay. Let me draw an axis system which is, say, okay. So say this is my axis system. There's a reason why I'm going to extend this a little bit. Okay. So this is actually my x. Okay. This is actually my x. Then let's just say that is y, and then that. Okay. Now so this is right, and then you have basically a flow coming in, right? So you have okay, so this is the flow which sort of comes in, right? Now this one, this is a flow which comes in, and let's just say that this one if I decompose the velocity in the three directions that I have, the components will be something like this. So this is your u, okay, this is your well, to give it a little different notation, right, and this is your W, right. So, these are the three basically the three velocity components. Okay. This of course is a nozzle, this is a nozzle. Okay. And then of course, you have flow coming out of the exit. So, you have an entrance here, right here, and then you have the flow coming out of here. So, let us just say that, okay, and I have flow coming out of here. Okay. So, let us just say this one is, this is essentially jet velocity. This is jet velocity and the diameter here. So, the diameter here is essentially, okay, this is d. This is the diameter which is d. Okay. So, that is that. Now, the question is that I just asked. Now, you have now what we have here, so we have the exit, the jet velocity or the jet exiting from the exit here, right, with the velocity uj. Now, the question is what happens after that? What happens after that? Okay. Now, this is highly turbulent flow. How do I define this? How, what is going to happen after this? Okay. Now, the question is how do I figure out also? Okay. So, if you have seen the jet, every time you have to draw a jet, how do you draw it? You actually draw some kind of a V. Why do we do that? It is almost kind of, we see that. So, now this is okay. Before I do that, let me also write what I am going to do here. Okay. So, this is what we it is important to write this here. So, what we are dealing with is round free jet. Okay. So, round because I am taking a circular cross section, it could be a square cross section for all you care. Okay. Now, free, what is so free about it? Well, once it leaves the nozzle, as you can see, once it leaves the nozzle, right, once it leaves the nozzle, then it does not have any physical boundaries to guide it. Right. Now, the point is when the flow comes into the nozzle, right, it cannot go anywhere other than the nozzle. It has to remain within the nozzle because it is guided by these solid walls of the nozzle. But once it comes out, of the exit, then what does it do? Then where does it go? Right. So, then pretty much it can actually go anywhere at once. Right. It really can go anywhere at once. Right. But it comes out with a certain kinetic energy. It has a certain turbulence in it, and I mentioned turbulence because it is a disturbance which is probably going to slow it down, right? We do not know. So, then in that scenario, how does this flow behave? How does this flow behave? Where does it go? So, that is our job to sort of figure out. Okay. Now, so in that context, let us just say that I am going to take a particular distance here. Okay. Let us just say this distance and say this distance is, well, this distance is actually x1, right. So, let us just say here the x is 0. Okay. So, we are going to call here this distance, this location. So, I am going to call x as 0, right. See, I have drawn the axis system here. Okay. So, so it almost seems like the origin is right here. So, you can actually think of the origin to be right at the exit for our use basically, or you can basically think that when I am considering the distances, I am considering it from the exit. Okay. So, when I say x is equal to 0, it might as well be just the length of the nozzle, but then for my considerations my 0 actually starts at the exit. Okay. Okay, and then this one is say x1, and let me take another one location, and let us just say this is x2, right? I take x2. Now the question is, how will this jet behave? How will the jet, now it has, once it has come out at x is equal to 0, how will it look like? How will the jet look like at x1 and x2, right? x1 and x2. Well, let's look at this one. So this is a side view of the velocity which is coming out of this exit, right? So if I were to look at the front view of that, how will that look like? Oh, right. So okay, so if I were to look at this, right, this is my jet exit. Okay, this is my jet exit. Okay, so in this case, let's just say this is x, right? And let's just get some polar coordinates in there, right? So this is essentially r, right? And this is making an angle theta, right? And so r is a radial vector, right? R is a radial vector, and the maximum distance, the total length, right, of this or the maximum r is basically r goes from minus d to plus d. Okay, if this is your origin. Okay, so this is essentially the diameter d. Okay, this is how I would look at it. Okay, this is how I would look at it. Now the question is, so how do I calculate, for example, u mean? So if I look at the x component of the velocity, say u, right, how will I calculate the u mean? Now, so if for example, let's look at it this way. Let's look at another side view force like that. Okay. Now, when I am going to look at the velocity, I am going to calculate the mean values, say. Okay. Now, I could look at several locations. I could look at several locations within this point, wherever I want. I could look at all these locations within, within the and more. There's all these random points where I'm looking at, and everywhere, it has a velocity vector. Everywhere it is a velocity vector. Okay. It's a turbulent flow, and I'm not exactly drawing, all these velocity vectors at the same size, or, So, essentially I will have this, right, so on and so forth. Now, this velocity is coming out, right, and if I am going to calculate this in a discrete manner, so velocity is coming out at all these points, and the magnitude I am assuming is not same. Okay. Then how do I calculate the mean? This is at a certain instant of time. Okay. At a certain instant of time, let us just say at some instant of time I have this, right. Then how will I calculate the mean of this? How will I calculate the mean velocity which comes out of it? How will I essentially calculate u mean, right? So, essentially all I do is take all these, values and take a mean of them, all these individual values of the velocities at several locations of x, y and z, and I calculate that, right, and I calculate that. Now, that is that. Okay. Now, there is, so this is in the sense that all these particles, okay, let me not locations rather. Okay. So, these locations are everywhere like this. Okay. These locations are everywhere. These locations are everywhere. Okay. Now, I could choose the r in several ways. Okay. So, when I calculate, for example, I am going to just redraw that because it has got congested here. So, if I am going to redraw this, so let us just say I have this somewhere over here, okay, and this is my x, right, and I am going to take these particular locations. I am going to take these particular locations, right, and let us just say I will take one here and one here. Okay. How do you locate this? So, I have a radial vector like that. So, this is going to be say r1, let this be say r2, okay, and this is at some x, because this x is along some distance from the exit, right. This is at some x, and this is the r. So, you define that by the r and the theta, that is how you define it. Now, how would you define it for say 1, 2, 3 and 4? How would you define that location? Well, that location, as you can see, r is 0 for 1, 2, 3, 4. Right, r is equal to 0 for 1, 2, 3, 4. Then, so then now if I take just those points, if I take only those points where r is equal to 0, right. So, r is equal to 0 basically means I am on this red line, which is the axis system, right, which is the axis of symmetry, which I have drawn through the nozzle and passed it, right. So, r equal to 0, r equal to 0 basically is the axis of symmetry, right, is the axis of symmetry, right, and these points 1, 2, 3, 4, and I have just shown you 1, 2, 3, 4, you can take as many points as you want. If they lie on that axis of symmetry, then what I get, right, then this one actually, in that case, this one, right, becomes some x, right, some x, and what is y? In this case, y is also 0. So, now r is 0 of course, and y is 0. So, here y is 0. So, y is 0, right, and you can take some z. So, for all practical purposes, we are taking z as 0 as well, right, this. So, this one is actually, so this one, right, this is nothing but center line velocity. Make sense? All right. So, essentially all I am saying is you take the mean velocity, right, you take the mean velocity at locations which are lying on the x axis, such that y is 0, and if I were to look at it in these coordinates, so basically the radial vector, radial vector is 0, right. So, you can take any point here, you can pretty much you can look at any point, right, and it will have some r and some theta. In this case, the theta is also 0 and the r is also 0. So, which means which lies on the axis of symmetry, which is r is equal to 0, right, r is equal to 0, and as well as let us also add there, and y is equal to 0, right. So, both of these basically means the axis of symmetry. Once I do that, so then I call that, so when I take only those points and I calculate the mean of the x component of the free stream, I get this. So, then I also write this as, so this is my center line velocity, and I write this as u naught. This is of course a function of x, this is a function of x. Okay. So, this is one definition which I had to we had to get it out of the way. So, this is number one, so which is just basically center line velocity. Now, okay, so now center line velocity, what do I do with it? Now, my first definition that I need in terms of round jet, because the question I asked was, once it comes out of at x is equal to 0, where does it go, right? Where does it go? Well, I mean, how will it look at x? all right. So, center line velocity, now I define something, let me first write that and then we will define it. Okay. We say what is called as a jet half width, it is a jet half width. Okay. So, at the center line I have the mean of the is a center line velocity u naught. Okay. Now, how do I define this jet half width? Now, I would think that as now what will happen here. So, you have probably you will think how will this jet move, do not we when we draw a jet do not we draw it like that, right. We think this is a jet, every time we draw a jet we draw it like that. So, let us just say that I do that. So, then it is like that. It is like that. Okay. Right. So, now here, okay, now the question is where should I have drawn this yellow line? I mean, where are the limits? How do I define this? So, the point is that the jet is spreading, right, there is a spreading. So, this cross section which I had drawn at x is equal to 0. So, now that seems to increase as we move along the x axis, right, the jet is spreading. Now, how do I define till what length is it spreading? Now, for that what we use is a jet half width. How do I define that? The way I define that is that this is, so the velocity here, right, here the velocity that I get is u naught x, right, x, which means u naught at x1 is different from u naught at x2, right. So, if I take these points, if I take these locations here, they will have a different velocity. If I take these locations here, these will have a different velocity, right. So, what I have here is say u naught of x1, what I have here is u naught of x2, right. Now, the location, the radial vector or the at some location where this mean velocity, is half of this, right, where the mean velocity of that location is half of the center line velocity, that is my corresponding r half, jet half width. Let me explain that. Okay. So, let us just say that I am going to take one of these. Okay. So, let us just say that I have something like this. Okay. And then this is my x. Okay. And as we have seen so far, if I can take these locations, right, where r is equal to 0 and here it is basically the central line velocity, right. Now, what if I take points somewhere here? What if I take these points? What if I take these locations, right? At these locations, as you can see, right, each it has a certain r, right, and they are all distributed. So, the theta will be different. So, they have the same r, right. Now, if for example, these are points, let us just say I am going to take say say A, B, C, so on and so forth, right, so on and so forth. So, A, B, C, D, E, F, G, H, I, J, say K. Okay. I have these points. Now, then I take a mean value of these velocities, right. So, I take a mean value of velocities at locations A, right. I take a, so let us just say I take a mean of the velocities u a, u b, u c. Okay. If I take, so this is has a corresponding r, this has a corresponding r, right. Now, if this velocity is equal to 1/2 of the central line velocity at this location. If this velocity, if u r, if the velocities that if the mean of the velocity is calculated at all these points which I mark by green is 1/2 of the velocity that I obtained by looking at these points which lie at r is equal to 0, if this exists, then the corresponding this r value then is called r half, and so this is the jet half width, right. So, I use this jet half width, so basically to study how much is going to be the spread of the jet, right. So, jet half width is basically r half. What is that r half? So, velocity, right, at some x, right, and r half, right, is equal to half of the central line velocity. Half of the central line velocity, what is the central line velocity? So, this central line velocity is nothing but x 0 0. Makes sense? So, the distance, the radial distance, right, r half at some location x is such that the velocity at the mean velocity at this point, at this location, at this distance is 1/2 of the central line velocity, right. So, as you can see that if the central line velocity here, so this might be so these might be those points, right. If these might be those points, then this is the r half, which is at x 1. So, r half therefore is also, therefore a function of x. So, similarly, if I go here, so then this might be the location, right. This might be the location where if I take the mean velocities at all these locations, right, then the corresponding r. So, this is the r half, right. So, r half is also a function of x, and this r half is actually used to define the spread of the jet. Okay. So, I need to calculate that. Okay. All right. Now, the point is, well, I think what we there's one more thing to say. Where should I first where should I start taking x, where should I start looking at, this has just come out at x is equal to 0, the jet has just come out of the exit. Where do I start taking x 1 and x 2? Well, there is a developmental length which is about 25 times the diameter. So, x 1 is usually taken beyond that. Okay. So, you will probably have a developmental length which is about this much. Okay. This is about this much, and this here x is greater than 0 and less than equal to 25 times the diameter, 25 times of this diameter, okay, exit diameter, and x 1 this is, and then this one is actually called the developmental length. Now, why is this important? Well, this is important because we think that in this zone, once the turbulent jet comes out, it's still sort of to exhibit this property that r half is going to, at distance r half is going to have half of central line velocity, and there are some spreading rate and etc. to calculate that to be, and this also becomes self similar, which we will learn later on. Okay. So, that behavior is going to be exhibited only after it kind of settles down a little bit. So, that settling down period, for lack of a better word I guess, is this developmental length, okay, which is about 25 times the diameter. Okay. All right. So, I think that kind of takes care of it. Now, the point is that let me make some notes, and then we are going to look at some of the experimental results already existing, and we will see what inferences we can draw from that. Okay. All right. So, some just notes to write down here. So, the note to write down here is, we have number one, because where will this get violated? When this is a description we did just now, that jet half width is going to give me an idea of how much the jet is spreading in the longitudinal distance. Okay. So, we have the same fluid inside and outside the nozzle. Okay. Yes, that is very important. The fluid is at an ambient temperature. Well, ambient actually conditions rather. Okay. It is at ambient conditions outside the nozzle. What does this mean? Well, this basically means that when, I think this is something I mentioned even when we were talking about when we were looking at the pictures. Now, when the fluid comes out of, when the jet comes out, right, there is no fluid flow already existing. This is the only fluid flow which is existing. Whatever fluid was there outside, it's all quiescent. Okay. Quiescent is in ambient conditions. So, essentially this basically means, I get that spelling wrong? Yeah, that's it. Okay, it's basically in stagnant conditions. Okay. Okay, and then of course the Reynolds number does affect, the Reynolds number does affect it. It depends on the diameter, the density, the fluid velocity, okay, the viscosity of course. So, this is to say that the Reynolds number is a function of the jet velocity, diameter and nu. Okay. All right. Now, what we are going to look at is something that is given in Pope, page 98 and figure 5.2. Okay. I am going to draw that figure, and what we are going to do is, so now we did look at this. Now, the thing is we've done this. Okay. Now, we are going to look at an experimental result and see what it is telling us, whether what we discussed just now, how does this sort of quantify, and what are, how are we going to do that. Okay. I just want to look at that. So, now once you make measurements, you should be able to see that. Okay. There is a reason why we kind of draw jets always like a V. Okay. So, I have taken two distances x1 and x2 here. So, this is the same thing. So, here also, so what is done is essentially, so you have this here. Okay. This is my jet. Okay. So, this is your diameter. okay, and okay, that, and we're going to take 3 locations. So x by d is equal to 30, x by d is equal to 60, and x by t is equal to 100. So these are the 3 locations we're going to take. Okay, so these are 3 locations we're going to take, and what are we going to measure? Well, this is what is measured. Okay, this is what is measured. So let's look at that. I'm going to draw this as best possible. Okay. 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 Well, I'm not happy with the way I'm drawing straight lines. Okay, let's see if I can do this better. Okay, let's try it here. Okay, that. Okay, that's not too bad. Okay, all right. Now I have something like that. What I have on the x-axis, is essentially r by d. Okay, r by d. So when r is equal to d, that's 1, right? Okay, so r by d, right, and then okay, let's just say, and this one is actually u mean by jet velocity, right? So the mean velocity by the jet velocity. Okay. Now so now you can see that I will basically, if I have plots here, okay, so let's just say something like that, okay, and there is, this is say about 0.1, okay, and this is say about 0.2. Okay. Now so these are curves which are, this is, like I said, these are from an experiment, okay, which is available at, Pope, as I said, figure 5.2. Okay. Now I have certain curves which look like this. Okay. Now let's just say I have this one. Okay. There is one plot like that. Okay. Now this is a plot which is, this is the plot I get if I plot u mean by uj against r by d for x by d is equal to 30. So this is x by d equal to 30. Okay, I get that. All right. Now, so what do I see here? Okay, before I draw the other 2 curves, I want to first decipher this. Now, let's just say that the maximum value that you see here, right? Now, on this axis, on the vertical axis, r is 0, which means that this is the center line, right? This line is actually center line, isn't it? This one is actually the center line, this one, isn't it? Because here r is equal to 0. Right, if r is equal to 0. So, if you see for x by 30 u bar, right, so you have so this is for x by 30. So, for x is x by d equal to 30, okay, is equal to say 0.25. 0.25, or you can say that this one is a central line. So this is actually u mean, right? This is actually a central line velocity. So I can actually write this as u mean, which is equal to 0.25 uj. Make sense? This is 0.25 uj. Okay. And this here of course is so that's that. Okay. Now let's just say that this is I'm also going to mark them. I'm also going to mark this. Let's just say this is point A and this is point B. Let's just say this is point B. Okay. So this U naught, right, this corresponds to, this basically corresponds to point A, right. Now the other one is UB, now where the velocity is basically 0, right. So I can say that U mean, right, U mean is basically equal to 0 and that corresponds to the point B, right. Now how do I find R half? Now R half is something where we get the velocity which is 1/2 of the centerline velocity, right. So what is the centerline velocity here, which is U naught right here, which is at A, right. So I should get 1/2 of that. So when I get, how do I get 1/2 of that? So let us see. I'm going to mark all these the R halves by the red. Okay. Now I should get half of that. So it's 0.25. So it should be 0.125 somewhere here, right. So you can see it's between, say well, let's call this as O. So half of OA, right, or you can say BA also, frankly speaking, the vertical distance. So the OA, half of that is about 0.125. So this is about 0.125, right. So this is 0.125 UJ. So the corresponding, so if I do that, right, my plot is not to scale, just to mention, all right. Then this distance, so this distance is basically my R half. So let me call, so this is my R half at x by d is equal to 30, right, x by d is equal to 30. So this is my R half. Okay. So where I get half the so this one, so right, so this R half, so you can see this corresponds to U naught by 2, right, which is U naught is basically A. Okay. All right. Now I have the next plot, so which I am going to write by blue. Okay. So this x by d is equal to 60. Okay, x by 2 is equal to 60. So the next plot, it looks something like this. It's somewhere here. Now the next plot looks something like this, something like that. Okay. And let's again say, call this as, say, A dash, this is B dash. Okay. So as you can see here again, right, so A dash should be, we can do some value there. Okay. Let's just say, since I'm doing it, let's just say A dash is 15, right. So let's just say x by d is equal to 60. Okay. Then uj by this is equal to 0.15. This is here also, this is at r is equal to 0, right. So this is at r is equal to 0, right. Or this is again the central line velocity, which is 0.15 uj, right, and that corresponds to A dash, right. And then I have B dash, right. So U mean, right, is equal to 0, right, and that corresponds to your B dash, right. And now, so I need half of that, half of this 0.15. So between 0 and A dash, so 0 and A dash, I should go where? So I should go somewhere here. So 0 and A dash, it's 0.15. Oh, okay. Yeah, so it will be somewhere here, isn't it? It will be somewhere here, this one, right. So this one, now I go that way, right. So, this one is basically r half at 60, right. So, this one is nothing but about so this one is about right. So, this is it. So, this is the r half at basically b, okay. And then again I have another plot which is, okay, let us see if I were to draw that. So, that other half, that is somewhere between, so somewhere from here. So, let us say from somewhere from here, and it is here, and this is for x by d equal to 100, and this one was x by d is equal to 60, right. So, x by d is equal to 100. So, again, so what does this mean? So, let us just say again I am going to mark that again, okay. So, this is say a double dash, say b double dash, okay. So, then x by d equal to 100, okay. So, what is that? So, u mean by uj is basically, let us just say it is about 0.07 at r is equal to 0, or u mean basically central line velocity is about 0.07 uj, right, and that corresponds to a double dash. Okay. So, that is my u mean. I take half of that. So, then I take half of that velocity. So, which is basically this, right. So, this is my r half, this is my r half at 100, right, because, and then this corresponds to, this is about 0.035. 0.035. Okay. So, as you can see here, let me, so this is my r half at x is equal to 30, this is my r half x is equal to 60, this is my r half as I go to 100. So, what do you see? So, if I had to summarize this, if I had to write this down, okay, let us do that. Okay. Let us do that. So, I mean, if I had to summarize this, well, if I, so what I see is basically from this plot, that if I increase, if I go along, if I move along if I move forward along the x axis, right, the jet is spreading. The jet is spreading because r half is increasing, right. R half is something that I am using to define, to sort of, let us just do that. So, this one here is one plot, is a spread, right, and the next thing is somewhere here. So, this is something which is spreading, right, and finally, this is somewhere here where this, right. So, essentially what I am having is this whole jet, right. So, with, as I move along in the direction of x, there is I mean the jet basically spreads. So, if I were to just in summary, if I had to write, so with increase in x by d, number one, the jet spreads. That is easy to see, right. Why? Because r half increases, does, right. You can see here for yourself. See, look at the, oh shoot, So, if you see here, the r half is basically increasing. Okay. So, r half here increases, r half you can see the length increases, length increases. Okay. Now, the next thing, what else do we see, right? When I move along, when I look at this central line velocity, now the question is, how is the central line velocity behaving, because my r half will depend on that. Okay. Now, if you see at x by 30, the central line velocity is here located at the point A, at x by 60 is located at A dash, which is less, and at 100 is located as A double dash, which means that the jet is also decaying. Jet is also decaying, in the sense the central line velocity is decreasing with the increase in x. Right? Is that a fair thing to write? So, the jet decay because central line velocity decreases with increase x, of course, yeah, with increase in. Okay. Well, I think we'll have to the spreading rate. Thing will be, how do we look at what rate is it spread? So, those are the kind of, and what at decaying. So, that's all. So, now I took random locations, and I can infer that as I increase x by d, my because the central line velocity is decreasing, also spreading because r half is spreading. Okay, how quickly, how fast, at what rate? So, that is something we'll do next to figure that out. For now, all for this. Okay. So, we'll stop here.